In this video, we're going to cover section 6.2, and we're going to learn the connection between right triangles and the unit circle, although we maybe saw that to some extent when we were filling out the unit circle the first time around. And so one of the first things that we're going to do is define some terminology here. What the hypotenuse is, what the opposite side is, and what the adjacent side is. So in this little diagram that we have over here, we have this angle theta placed right here. And so opposite of the angle is what we call the opposite side. Okay. Now there are two sides that are next to the angle theta. One of them is the hypotenuse, which is the biggest side of the right triangle. And the bottom side at the moment here is the adjacent side. And we could or not reorient this triangle, but we could make another triangle here just to emphasize what these definitions really are here. Let me see if I can tilt that up here a little bit. Go. All right. So if I were to fill in here that this is a right angle, and this time I'll put the angle theta up here, then is what's going to happen is we'll call the side opposite of that angle, we'll call it the adjacent side. Let's go ahead and write that in here, adjacent. Or I'm mistaken there. Opposite of the angle, we should write the opposite side. That would make a lot more sense. Okay. The hypotenuse is still the biggest side. And then lastly over here, this is the adjacent side. Okay. The side next to the angle theta that's not the hypotenuse will be the adjacent side. Okay, and so we're going to use this terminology here in a minute or so. So is what I want us to do is imagine that we have some angle. Maybe it looks something like this. And you could imagine that we could form a little right triangle here. This is what we did when we were filling out the unit circle, was imagining a triangle like this. And if we know that this point up here is, say, x comma y, well, then we know the height of this triangle is y. I'm going to write that in here. And we know that its base is length x. And so what I want you all to do is now think about this smaller triangle here. I'm going to call this x. I'm going to call this y. And then we have this bigger triangle that's similar to the smaller triangle. And so is what I'm going to do here is get another color, and I'm going to label the side lengths of this big triangle here. I'm going to call this side A, or let's call it let's call it A for adjacent. Let's do that. A. Similarly up here, I'm going to call this side here the opposite. And I actually haven't written in the angle yet, but our angle right was this angle theta. There we go. All right, so I'm going to write a capital O here for opposite side. And then we know that that longest side that I haven't marked yet is our hypotenuse. And I'm going to try and label this here neatly. So I'll write in maybe a capital H here for hypotenuse. There we go. And then there's one last thing I want to actually label here. So we also know that this side length right here is 1 because this is on the unit circle, which has a radius of 1. So that means I could also go over here and I could label this as a 1. All right, so now that we have this, again, we have two similar triangles here. So here's the trick, okay? And it is that if we're looking at sine of theta, right? Well, that should be the y value here, okay? Now, what's not clear is that I could write this actually as 1 or y over 1. Okay. And so notice is what I've done is I took the opposite side and I put it over the hypotenuse. Okay. Is what I've technically done there. All right. And now because these are similar triangles, okay, if I were to do the same thing with the big one, their ratios should be equivalent. So in other words, if I take big O, I could put that here and then over big H. Okay. So when we think about sine of theta, if we're not on the unit circle, let's say, maybe we have some triangle that's bigger. Okay. Well, we'll know that sine of the angle is equal to the opposite side over the hypotenuse. So in other words, we don't need to always be working with triangles that have a hypotenuse of 1. It could have some other hypotenuse. Okay. If I go down here to cosine, I can do the same little trick here. I can say, well, I could rewrite that as x over 1. And if you notice, that's really the adjacent side over the hypotenuse this time. Yeah. And that being said, these ratios should hold because we're going to have similar triangles. So I'll have my adjacent side over the hypotenuse. And then finally on to tangent, which is y over x. Okay. So y over x should give me the same thing as if I do the opposite side over the adjacent side. Okay. So opposite over adjacent. Okay. And I can do now the same thing for the rest of these. But remember, these are all reciprocal functions. So cotangent of theta should be equal to the adjacent side over the opposite side. Okay. Cosecant, okay, should just be the reciprocal for sine. So hypotenuse over opposite. Okay. And then lastly, secant, this should be the reciprocal of cosine. So this is going to be hypotenuse over adjacent. Right? And we do have a mnemonic device to remember this. So I actually only ever remember this relationship for sine, cosine, and tangent because I can get the other three by just writing down the reciprocal for sine, cosine, and tangent. But the mnemonic device that I'm going to be saying is SOH-CAH-TOA. And so is what this is. Let me try to make this look a little bit neater. There we go. Is what this is telling you is that sine of theta is opposite over hypotenuse. Cosine of theta is the adjacent side over the hypotenuse. And tangent is the opposite side over the adjacent side. And so this first one here says find the value of each of the 6 trig functions. Okay. So one thing we could do right now before we start finding all 6 of those trig functions is I do notice we have this missing side over here. Okay. Well, we could find that missing side actually just using our Pythagorean theorem. So for instance here, I could say maybe that this is y. And so then I have 4 squared plus y squared should be equal to the hypotenuse squared. And then is what we can do is we can grab our calculators and we'll do 5.7 squared. And what was that? And then minus 4 squared. Yeah. And then we do want to take the square root of this, although I don't know that it's going to come out extremely nice. It doesn't. So I'm just going to write the square root of 16.49. I could check real quick if this could be written as a fraction. It can't. Okay, so yeah, just the square root of 16.49. There we go. So now that we have all those sides, we should be able to come through and find, say, sine of the angle C. So as what we learned was that sine, so if you think about SO, right, our mnemonic device, sine should be opposite over hypotenuse. So opposite of this angle is y, and then over the hypotenuse. Now I do know what y is though. I can actually write that in. So I'm going to do that. Uh, this means we can very quickly then find the value of cosecant of c. It should just be the reciprocal. There we go. Now we could try cosine of c. So cosine is supposed to be equal to the adjacent side over the hypotenuse. Adjacent over hypotenuse. So this is going to be the adjacent side. And then if we divide by, it's 5.7. Which would mean then we could find secant of c very easily here now. Secant of c is going to be just our reciprocal here. So 5.7 over 4. And so we just have two more to go. Tangent. We learned that this one was opposite over adjacent. So the opposite side is y. Let me write that just a little bit neater, 16.49. Okay, so there's my opposite side. And then I want to divide by the adjacent side, which is 4. And so this also means that cotangent of the angle C then would be 4 over the square root of 16.49. There we go. So let's go ahead and give another problem a try here. So this time we want to find the measure of the side of the right triangles whose length is designated by a letter round to the nearest whole number. So we're trying to solve for x here. So we want to think to ourselves, if this is our angle, well, what do we call these two sides? Okay. Well, we call this one the hypotenuse. We call this one the opposite side. And so we need to ask ourselves, what trig function involves the hypotenuse and the opposite side? Well, that should be sine. Sine is opposite over hypotenuse. So what this means is that I could rewrite this as sine of my angle is equal to, again, the opposite side over the hypotenuse. And so I just need to solve this equation here for x. So I could multiply each side of that equation by 41, and I'll get x is 41 sine of 25. And so then we just want to plug this in our calculator, but do note this is in degrees. So make sure your calculator is in degrees first. I'm going to shrink up, scoot this over and then shrink up my calculator a little bit. Okay. So we wanted to plug in 41 sine of 25. and just double check real quick, hit mode, double check you're in degrees. I'm in degrees here, so I don't need to go reselect it. So I'm going to go ahead and just hit enter here. And so I'm getting about 17.3. And we were told actually to round to the nearest whole number. So I'm going to just round this to 17. Right, and that's all we'd have to do there. So let's go ahead and scoot down and we'll try another one. And again, round to the nearest whole number. So this time we want to find the value for k. And so we have our angle. And so we just need to remember what these two sides are called. This one is the adjacent side. This one here is the hypotenuse. So we need to ask ourselves what trig function involves the hypotenuse in the adjacent side. This would be cosine. Cosine is adjacent over hypotenuse. CAH, C-A-H. So I'm going to write cosine of the angle. And again, cosine is adjacent. So that's the 45 over the hypotenuse, which is k. And in order to solve this for k, I'm going to multiply both sides by k first. And then to finish solving for k, I'm going to divide each side of the equation here by cosine of 53. There we go. And so once again, I'm going to scoot this over and we can plug it in and we'll round again to the nearest whole number. So we have 45 divided by cosine of 53. And if we round that one to the nearest whole number, that's going to round to about 75. So we can go over here and record that. Maybe I'll box my previous answer here too. Oh, I already did. Okay. And then we have one more we're going to do. So this time we need to focus in on our angle. And if we look at the sides we have the the opposite side and the adjacent side. So we are going to be using tangent. Tangent is opposite over adjacent. So I can go in here and I can write tangent of my angle is equal to, right, TOA, opposite over adjacent. And again, I want to solve this for x, so I'm just going to multiply each side by 14. There we go. And we'll go ahead and we'll plug that in the calculator and round it to the nearest whole number. So we have 14 tangent of 67. And so I'm getting about 33 if I round that to the nearest whole number. All right, now we've found missing sides. You can also find missing angles. And so let me see how many examples we have left here. Okay, so we'll get a chance to do this. It looks like at least a couple times. But let's say we have this equation that we want to solve for theta. And 0.8771 is not one of those numbers that we're used to seeing as the x or y coordinate on the unit circle, right? We're used to plus or minus 1, plus or minus root 3 over 2, plus or minus root 2 over 2, plus or minus 1/2, and plus or minus 0. And this is not one of those. So the unit circle doesn't exactly help us here, but we can use our calculator for this. You could actually solve this equation for theta by taking cosine inverse of each side. And so when you take cosine inverse of cosine theta, those two things undo each other. Now I should be careful. They undo each other because we're told theta is an acute angle, meaning that this angle is in the first quadrant, and cosine inverse can give us angles in the first quadrant. So this gives us theta equals cosine inverse of 0.8771. And let's go ahead and plug that in. And it does say to leave our calculator in degrees for this one. So what was it? Cosine inverse of 0.8771. So this one here says to, let's see. It doesn't say what to round to here. So let's just say 28.7 degrees. There we go. Let's just double check that. 28.7. Okay. All right, there we go. So that's all we would need to do for that. Let's take a look at another one. So once again, we want to find an acute angle. And luckily, tangent inverse can give us angles that are acute. It can give us angles in the first quadrant. So we'll go ahead and we'll take tangent inverse of each side this time. And remember, the tangent and tangent inverse are going to cancel there because we know that this angle is acute. And so let's go ahead and plug that one in too. Let's see. So tangent inverse of 0.5117. And so here we're getting about 27.1. Now that's in degrees. Let's see if this question mentioned anything about the units. Yeah, so we need to change that. So I need to go mode, come down to radians, hit enter, second, and then mode for quitting. And then I can just hit second enter to make my previous line pop up and hit enter here again. And so actually this comes out to about 0.47 radians. You know. All right, now I do have some notes to make here about our inverse trig functions. So unfortunately, this notation is confusing. It's confusing because we're saying that this is the inverse function, which looks a lot like the reciprocal of tangent. So, right, the reciprocal of tangent, you could write like this. And by reciprocal, all we really mean here is that this is equal to 1 over tangent of x. Okay. So these two things here mean the reciprocal of tangent. Meaning really that those two things on the right are equivalent to cotangent for most values of x. But on the other side, which let's see, let me get a different color here. On this side, this is talking about inverse tangent or tangent inverse. So the only other thing I'm going to note here is that for these inverse trig functions, when we go to write them, we will typically write them in the fashion that you see here. But some textbooks like to use arc sine instead of sine inverse of x. it means the exact same thing. It's just I would consider this an older notation, but it does have a benefit. Its benefit is that we won't mix up now the inverse with the reciprocal. Okay. So there is a benefit to that notation, but we probably won't see it a lot. Okay. And then before we do a couple examples here, when we talk about angle of elevation, this is just simply how far up we go off of the horizontal, versus angle of depression would be how far down we go off of the horizontal. All right, so let's try a couple out here. So it says when the sun's angle of elevation is 57 degrees, a tree casts a shadow that is 30 feet long. Find the height of the tree. So if we want to do that, we again need to look at our angle. We may also note that we have this missing side over here. I'm going to label it, let's just label it maybe with an H, a lowercase h for height. Okay. So that H over here is our opposite side. This is our adjacent side. So that means we're working with what trig function? Okay. And so that trig function must be tangent. So I have tangent of my angle is equal to opposite over adjacent. Okay. So to find the height of this tree, I just need to now multiply each side by 30. And so I get h is equal to 30 tangent of 57. Now in the last problem, we had our calculator in radians, so we need to switch that back to degrees. So I'm going to hit mode, go down to degree, hit enter, and then second mode to quit out. And let me scoot this over a little bit and we'll get this plugged in. Here we go. So we said we have 30 tangent of 57. And so that's giving us here, we're going to round it to the nearest tenth. So that's the first decimal place. So this is 46.2. And this is measured in feet. Okay. All right. And so we're going to just do, I believe I just have one more example in here for us. So this time we're looking for an angle rather than a side length. And so we have somebody on a ladder. That ladder is reaching 15 feet high on the wall, while the base of the ladder is 6 feet from the base of the wall. Well, if we look at what sides we have relative to this angle x, we have the adjacent and opposite sides again. So we will be using tangent. So I have tangent of my angle. And you can see in the diagram, this angle is an acute angle. So when I do go to take tangent inverse of each side, I don't have to worry. Tangent inverse can give me acute angles. It can give me angles between minus pi over 2 and pi over 2, or if we're in degrees, minus 90 to 90. So this is perfectly fine. So our adjacent side is that 15. Our opposite side is the 6. And so x here is going to be equal to, let's see, tangent inverse of 15 over 6. I'm going to get rid of this degree symbol here at the moment. It's kind of bothering me. I'll write degrees in here for our final answer. So tangent inverse of 15 over 6 is approximately, and we're going to round to the nearest degree, tangent inverse. See, it's second and then the tangent button. And 15 over 6. So we're getting about 68 points, or about 68 degrees. Right. And that would be all we'd have to do for this one. Oh, there is one more topic we're going to mention, and it will lead us into the topic that we'll do in 6.3. Another way that we can use these triangles, and in fact, I'm going to sketch one over here first on the side. In fact, I'm going to sketch it this way because this will be how we would have seen it earlier. Okay. So we had a special right triangle that we used, in fact, two of them to construct everything on the unit circle. So opposite of the 30, we had a 1/2. Okay. Opposite of the 60, we had a √3/2. And for the hypotenuse, because this was on the unit circle, the hypotenuse was 1. Okay. Now, there's nothing wrong with this triangle. We can actually use this for what we're about to do. However, I think that there is a more convenient way of using this triangle. So we're going to use a triangle that's similar to this one. In fact, I'm going to double the side lengths on this triangle. So if you double the hypotenuse, that's going to give us a 1. So I'm going to go over here and write in a 1. Opposite of the 30-degree angle, again, is 1/2 at the moment. But if I double that, opposite of the 30 should be equal to 1. Okay. And I think I did some bad multiplication over here for the hypotenuse, right? The hypotenuse was 1, and if I double it, that would give me a 2. That makes much more sense. Okay. And then opposite of the 60, we have a √3/2, and if we double that, we just get √3. So I'll get a √3 here opposite of my 60. Now, of course, we could write this in radians as well. Maybe I'll just write in √3, 2, and a 1, and then we'll change the angles to radians. So this will be the pi/6 is 30 degrees, pi/3 is 60, and then our 90 is still here. We're going to do the exact same thing down here for the 45, 45, 90. And you know what? I'm going to just copy the one that's already here now that I see it. Let's go like that. Okay. So when we first learned about the 45, 45, 90 triangle, again, we were on the unit circle, so the radius was already a 1. And the side lengths were √2/2. So if I double all my side lengths again here, this will become a 2 here and here. And the other side lengths were √2/2. So if you double √2/2, you just get √2. There we go. And then if I want to write my 45-degree angles in radians, it's going to be pi/4. There we go. So it ends up that now we can use these triangles to evaluate our trig functions. So if you prefer to think about triangles as opposed to the unit circle, you can. And let me show you what I mean here. So sine of 45. Well, I could just find a 45-degree angle up here. And I could look at the opposite side over the hypotenuse, right? Sine is opposite over hypotenuse. So that'll give me √2, and then over the hypotenuse, which is 2. This is exactly what we would get if we were using our unit circle. Similarly, for tangent of pi/6, I just need to go over to the triangle that has a pi/6 in it, okay, right here. And so tangent, right, is TOA, opposite over adjacent. So that would be 1/√3. Yeah, opposite over adjacent, 1/√3. Okay. And if you were to rationalize that, right, you could multiply both the numerator and denominator by the square root of 3, and we get root 3 over 3. Okay. And then lastly, cosecant. So is what I usually think about first is I'll usually think about sine, which is opposite over hypotenuse, right? SOH, sine is opposite over hypotenuse, which would mean that cosecant then is hypotenuse over adjacent. Now we do need to go look at the triangle that has a pi over 3 in it. So right here. Okay. And right, we said first we're going to have the hypotenuse on top. So the hypotenuse is 2. So I'm going to come down here and write in at 2. There we go. And then the adjacent side to pi over 3 is the 1. So we just get 2. And this makes sense. Sine of, let's see, does that make sense? Sine of pi over 3. Did I mark that right? Let's go back up and just double check here once more. So the hypotenuse, we said was 2. And the adjacent side was 1. Something just feels a little off to me here. So, um, that's what it is. I think I had originally written that sine, right, is opposite over hypotenuse. Well, cosecant then should be hypotenuse over opposite. That's why this isn't coming out right. Okay. So my opposite side is not 1, it's root 3. Let's go put that in here. Okay. And if you wanted to, you could rationalize the denominator here. You could multiply the numerator and denominator by root 3. And that would leave us with our final answer there. And so this wraps up section 6.2.